First and foremost, I will thank the organizers of the program for inviting me to interact with you guys. All of us are students because we still read every day. We work every day. So we are students. So don't be amazed or whatever I'm referring to their colleagues. Okay. Now, the second phase of all these are lectures. As you know, it's a research-oriented program, which means there is a level that you know already before coming into this program. And then, the topics and the tools are not that difficult. All that I know in your programs, you may have done a vector analysis, vector identities, and also you know how to operate on differentiation, partial derivatives that will take you to partial differential equations. And then I believe also you know a little bit of a numerical analysis, numerical techniques. Anyway, because you cannot do theoretical physics without knowing elements of numerical computation, because you need the numerical results to be able to interpret your physics. Anyway, as we go on, we'll get to know the tools that we'll require in this course. Okay, I'm going into magnetohydrodynamic waves with applications in the solar atmosphere. MHD waves. Next slide, please. We may begin to know what is MHD. No, the next one. MHD. We try to look at MHD is the dynamics of an electrically conducting fluid. Is what? Electrically conducting fluid. And these fluids are ionized. They are partially ionized or fully ionized. And when we come to that ionized gas, it's a plasma. All right? And then under the concept of quasi-neutrality, where the mass density of the neutrons are the same as the mass density of ions, they are equal, then we can consider what we call a single particle fluid dynamics. And in that case, we look at that as electrically conducting fluids in the presence of magnetic fields. Magnetic field is everywhere. Even as you are standing on the floor, you have erect connecting magnetic fields, field lines. So when you have a fluid that is in motion and you couple it with Maxwell's equations of electrodynamics, the marriage becomes electrically conducting and is regarded as magnetohydrodynamics. Put in another way, MHD is a mathematical model. So those of you who are looking for mathematics, it's a mathematical model that actually describes as microscopic behavior, that is large-scale processes in fluid coupled to Maxwell's equations. So we're going to look at that as fluid and Maxwell's equations. MHD is fluid plus Maxwell's equations. So when we look at this, you will see that MHD of a perfectly conducting fluid in the absence of electrical resistance when we don't have electrical resistance, we regard such MHD as what? Ideal. We have ideal MHD. In the time we go on, there are things we call dissipating parameters. We'll come to that as we go on. So that is no dissipation. No dissipation. Because dissipation actually generates heat in the system. But when we look at this MHD, we'll try to look at the areas where there are no dissipation, and we look at them as what? Ideal MHD. I don't know whether we are okay with the definition. It's simple. It's a description of electrically conducting fluids. We look at them partially or ionized, and they constitute what is known as what? Plasma. Now, we will try to look at the second stage. Next stage, please. What are plasmas? We mention the plasmas. What are they? You can see that plasmas actually composed of particles. They are what? Particles. In which electromagnetic theory is relevant. And both in the micro and macro, where you have this conducting fluid with electrical conductivity or magnetic fields being present in the system, is what we look at as plasmas. And if you follow the history, plasma is the fourth state of matter. You will see, how many do we have? Is the fourth state of what? Matter. What are the other three apart from plasma? Liquid and what? Gases. Plus this one, that's the plasma. Plasmas are actually a unique state. They are unique in the sense that they describe ionized gases. And I've said when it is ionized, the mass of neutron and that of ion are the same. They are equal under quasi-neutrality. Now, plasmas are greatly influenced by magnetic field. So, when we talk about plasmas, magnetic field must be present. High temperatures must also be what? Present. And in cases where you go, if you look at the thermodynamic properties, coupled with the Boltzmann's constant, we now begin to talk about optical depth. Optical depth. Is it optically thin? Is it optically dark, thick, gray, and so on? So these are kind of plasmas. But we need some things. I'm not going to talk about them. They are clearly written, which you can do, which you try to read yourselves. Okay? There are certain things that also look at, we call collective behavior. When we try to describe what constitutes a plasma, collective behavior is very, very important. It's a phenomenon in which the whole plasma behaves independent of the behavior of each particle that constitute them. It's what we call collective. So you are seeing them as a single, not individual particles coming into. Just like in fluid. When we look at fluid, they constitute particles. But as an embodiment, we look at them as a single fluid particle. So collective behavior is important as one of the characteristics that can define a plasma for you. Then there's also what we look at, which is very, very important whenever you are trying to describe plasma. Quasi-neutrality. Although when you go to we have one fluid, we have two fluids. But in this course, we restrict ourselves to one fluid as a beginner. Okay. Now, quasi-neutrality is very important. Because if they are not quasi-neutral, then we now begin to talk about multi-kinetic theory comes in. But now we try to restrict under the ideal MHD, where the phenomena of quasi-neutrality plays a great role. And when we now begin to look at this, there is a kind of imbalance created in the system, because they are trying to make sure that the electrons are fused out so that you can have an embodiment of the nucleus being controlled by the neutral species. That will lead us to the Debye length. You have Debye length, you have Debye shielding. Now, but the Debye length is very important. It's given by that. You can see chain. Maybe at the end of the class, I have the materials to give you the books. You can acquire so many. Okay. Now, this length we call under D is the Debye length. And one of the characteristics for it is that it must be far less than the length of the actual environment of the system. Is stated there. There is also a parameter in which the number under the Debye length must be far greater than 1. I've talked about collective behavior. All right. Now, there is something that we call plasma criteria. What are those criteria that will tell you that ionized gas is what? A plasma. What is that? We begin to talk about the collision time. Because this plasma we are talking about as we go on in terms of our waves, our processes, the wave processes. Okay? I've said that collective behavior will arise because of charged particles interact through long distances of electromagnetic forces. And then the disturbances, because when we want to talk about these waves, we talk about disturbances. So these are things we will try to come across as we go on. Now, because when you look at this collective behavior, it's actually a response to perturbations. Small changes in the original, in the static, creates perturbation. And what are those effects? The response to it will actually create what is coming out as collective behavior. Then the physical description of plasma will require, we can go in length scale, we can look at time, we look at maximum number of charged particles by unit volume. So it is important, this is actually an important criteria that must be met for you to consider an ionized gas as a what? A plasma. So all these things are the characteristics that we have to overcome for us to look at this as what? A plasma. Now, I said something about oscillations. I will read. You see, the time required for these oscillations to occur is one of the most important temporal factors in plasma. These oscillations can only develop if the oscillation period, TP, is short compared to the time between the collisions. Because the particles are supposed to collide. But what happens is this. The neutral particles, the ionic particles, and electron particles, like we are not coming into, because when we now begin to quantize them, we are now going to photons and fermions. You understand? So when you now look at them, there's a separation that's already occurring under the process of rotation. Oscillations are waves. So there is a time for it to complete a circle. And in this time, it tries to shield all the electrons that in fact you are left with only particles, and they cannot collide. Positive will look for negative, but when you have only positive, it becomes collisionless. So you can see where the demarcation is, and which is one of the criteria. Like, I've been to Padova, where you have a European community, that is CERN, where they're working on, they are working on how to produce energy from the fourth matter, from the plasma. And the whole of Europe, when they want to test, they will put the electricity off the whole Europe for 2 minutes. So you can imagine, and take all the energy to start off, to celebrate it. I've been to the cyclotron. Yes. So you see, that is the plasma. But what we are trying to do here, we want to ignore those, for those who are doing experimental plasma physics. And then we'll come to use our ideal MHD, which is a mathematical description of the phenomena we want to do. So you will begin to see wave. I know you know your wave equation. How many of us know wave equation? Say u x of t by t squared is equal to c squared of u of x of t. That is, that's a wave. We can modify it to Helmholtz equation, and so on and so forth. So, this is very important. This is also important because the length scale L must be far greater than Debye length. It's one of the criteria for plasma to be considered as what? Ionized gas. Anyway, we'll try to look at ideal MHD and see what will come out. There are a lot of volumes of work. Research topics are, I would say, infinite in this area. Only thing it requires is patience and some mathematical skills. We'll get there. All right? Now, but before we go, you will see that our interests will actually be solar atmosphere. We want to see the processes and activities that goes on in solar atmosphere that are actually as a result of propagation of waves. Propagation of what? Waves. So, we will look for a little bit brief on solar atmosphere. We may ask ourselves, what is solar atmosphere? You know, you have the sun. Yes. Go ahead. I understand what they're saying. Sit down. You see, like here, there are two things we do. Scattering is eliminated here. In what we are talking about, scattering is allowed. So we try to remove such things. That's why we are considering ideal MHD. We call it ideal, where dissipative terms are what? Neglected. Because those, when it's scatter, when there is collision, it will generate more heat, is it not? Into the system. And already, the temperature of the atmosphere we are talking about, some of them ranges, like corona, gets up to 20 million Kelvin. And then if a particle exists in such an area, it must be regarded what? As single, which is collisionless environment. But when we go, as we progress, we go into the waves. What are the consequences of these waves, emerging waves? They can generate what is called, known as a coronal heating. Because the phenomena that exists is that the sun itself is a nuclear reactive core. There is nuclear processes taking place. There is also radiative processes. There is convection. Before you now start coming, that's what we will try to do now. Okay? Now, what happens is that corona, the temperature is low, lower than what? The sun. All right? But when this radiation or this is convected to the surface of the sun, it's expected that as the height or the depth increases, temperature will reduce. But suddenly in the corona, there is upward temperature, heating. What are the causes of this heating? And then one of the things that can generate such heating might be as a result of a wave transport of energy by this distortion we have in the waves. We'll come over to that later, but we'll go on. They seem similar, but there are parameters that are not there. Okay? Laboratory plasmas are different from atmospheric plasma. But all of them work under the same principle of what? Ionized system. You know, in a laboratory system, you cannot have complete ionization. It is very difficult for you to have complete ionization. Do you understand me? The neutrons must be there. The ions must be there. The electrons, protons must be there. And then each of them have their own characteristics. It's just like when you go to remove an electron from each shell. You see, no? It takes a lot of energy to do that. But here, all those energies are gathered together because of quasi-neutrality. Okay. Now, we try to look at the solar atmosphere, which will be where we'll be taking our walk as we progress. I'm not talking about the interior of the sun, the core. Let's look at the surface, because surface is more interesting to us, because it's from the surface the parameters for weather forecast are gotten. It is from the surface that we now begin to have the existence of some energies that are coming from the sun. Electromagnetic radiations are coming from the sun. But how do we treat them? See, the surface of the sun or the atmosphere, we say they have particularly 4 distinct layers. These layers might go kilometers, hundreds of kilometers apart from each other. So we look at the solar atmosphere is composed of multiple layers. There are what? Multiple layers. And the lowest of them is the photosphere. When we look at the photosphere, is the lowest. And that's about the thickness of 500 kilometers. And then all the light that are actually visible from the sun comes from this layer. So the visible lights we are seeing are actually from the photosphere. And then in this place, the optical depth, what we call optical depth of this depth is actually less than 1. That is why we try to see that this light, we can see them with our naked eyes. You may ask me a question, what is an optical depth? Huh? Since you are not asking me, let me ask you. What is an optical depth? Well, it's a fraction of photons that can pass through a layer without dispersion. So it passes easily without what? Scattering. And that layer is the photosphere. 1/3 of the photons will pass through this unhindered, and that is why we can see them. They are visible light. When you go to the light spectrum, you will see the light you are seeing permeates through the photosphere. There are other characteristics. Well, you will see in the photosphere that sunspots also happen, but we are not going to talk about sunspots, just to mention them, so that at least let us begin to see the solar atmosphere, the sun's atmosphere. We are enjoying the sun, so let's see how it is getting to us. Otherwise, there are dark spots. There are things that could seize it. You know, the eclipse. When eclipse comes, if you have total eclipse, the sun, you are not seeing it, but it's shining in another world. Okay. Now, the darker regions of the sun's surface, why do we say that some of the areas are dark and some are light visible? So these are things you should look at into characteristics. They are contained in my note anyway, just that I'm trying to see how we'll go. So that, because we have to build on our waves before we understand that. Okay. Now, chromosphere is another area. Chromosphere is also visible as dim red ring that lies above the photosphere. What are the characteristics? They are only visible or experienced during solar eclipses. So you can now see when the photosphere is hidden, visible light from the chromosphere can be seen. So these are one of the layers. You will see what is solar eclipse. What is solar eclipse? There are some of you who say that it's in solar. That's UNN. I think you. Because I work with CBSS, and currently I have a PhD student. He's been able to identify some stars through experiment, through observation, that is currently published. I think this month we have it from one journal. So what is solar eclipse? The moon will pass between what? The sun and the earth. So we say you have an eclipse when the moon eclipses the sun, which means it's moving between the sun and the earth. So it will shield the light coming. It doesn't occur all the time. It's just periodically. But what happens in observation is that they constantly observe the weather to see when they will have the eclipse. And they use it to forecast for you. And do a lot of simulations. And take it from the last eclipse to the first eclipse. So they'll be able to tell you in 2014, 2024, you will experience eclipse by this time. That is what happens in observatory. Have you been to any observatory? So you try to go to South Africa. That's where we have an observatory in Africa. All right. Well, the chromosphere, its temperature will increase with height because a lot of materials are being convected, transported, radiated to come to that place. Well, you see that we also have a place we call transition region. Transition region. It's about 1 kilometer. The depth of the transition region is about 100 kilometers. It's regarded as a thin layer because others are bigger than it, much larger than it. It's above the chromosphere. So you have the photosphere, you have the chromosphere, you have the transition region. So you have the chromosphere, you have the transition region, then the corona. In fact, by the time we will start talking about the corona, you will know why scientists study about corona. I started studying corona in 1999, where I did gravitational stability of the solar corona. Okay. Now, you will see the corona itself is the outermost solar atmosphere. Its temperature is about 1 million Kelvin. And then, during some processes that might take place, it could go up to 2 million Kelvin. So you will see, at times it can get up to 10 million Kelvin. And the question scientists are still working on till tomorrow is what causes the solar corona to do what? For its temperature to increase. What makes it hotter? And after a while it will come down. When there is coronal mass ejection, it will come down. And after a while it goes up. Then what is the phenomenon? There are a lot of thoughts, school of thoughts, two of them. As we go on into the course, we now begin to experience them. All right? That is what happens in solar corona. Now, we'll try to see. Wave is what we are going to do. What is a energy wave? Let me ask that question. And then, or before I do that, coordinator, or the organizer, I hope, are we doing well? If you are not doing well, call me back, because I like my students to study. This is not an undergraduate class. All right? I'll give you the references. Okay. Now, you see, the sun creates a large amount of energy. The sun does what? It creates a large amount of energy. And emerging waves are thought to move this energy, either by convection or by whatever means. That energy is what may, I didn't say will, may do what? Influence the rise in temperature in the corona. All right? Okay. Now, as we look at the corona, there are quite a lot of studies and a lot of things that happen in the corona. We have the coronal loops, which actually goes on. There are loops. For example, if this is a foot, this is a foot. These are magnetic field lines. And then if you have a complete loop, it goes under the process of what we call reconnection. So that's also the field lines are. There are things to be done on coronal loops. And each of these are actually constituted tubes, what we call tubes in the atmosphere. But you can see there's a tube here. There's also a tube here. They have their magnetic fields. They have their magnetic field strength. You will see each of these tubes will be like this. They will reconnect themselves. And you know that the field lines have a property that never crosses each other. Is it not? Now, you will see this in the atmosphere under these tubes. And there is what this place that is open is actually called coronal holes. No magnetic field that is here. And it's because of the absence of magnetic fields in these holes that they propagate radio frequencies. You see? So each of the holes created, scientists, those of them that are in radio astronomy, they've been able to characterize these holes and get their frequencies. And these frequencies are apportioned to people to propagate their waves. That's how you have radio signals. You have these. They're all from the coronal holes. So coronal holes or the loops are also important phenomena. So those of you who are trying to look at the loops, coronal loops, are good as a research area that people are working on. Now, we try to be a little bit brief because I want us to finish and go and eat and go home and come back tomorrow. Not for warfare, but we are coming back tomorrow. Now, I will ask ourselves, what is a wave? Because that's where we're going to go. What is a wave? Please, the next one. Let me try. What is a wave? Are they tired? When we go to Grandson, when we go to ICTP, you learn from 95. And your directors will wake you up in the night. What is a wave? Aha! The solutions are there. When you look at a wave, is the transport of what? Disturbance. When things are moving, if you don't disturb them, what happens? How do you disturb? We now say disturbance, is it not? What is this disturbance? Now let's say you have a guitar. They have strings. As they are, there's nothing they are doing, is it not? But the moment you pull the string, you have distorted it, is it not? What do you see? What do you see? You start seeing things like this. Is it not? Huh? Is it not? It is this thing is what? A wave. It's moving in that direction. And it is what at the end of the day will produce what? Sound. So we describe a wave as transport of disturbance. And that disturbance is what? Contains information or energy. From, actually we must have a continuous medium through which they can move. And what do? They will convey that information from place to place. That is simple disturbance that you have created. And then in our system, how do we create the disturbance? You can see something that is at rest. Let's say arrow 0. We use 0 to represent rest. And then when you disturb it, let it become arrow 1. Is it not? So this one is the disturbed state. And this one is what? Undisturbed. Undisturbed. And you will see that if R is actually, you have arrow 0 plus epsilon arrow 1. We are going to use a little bit of perturbation. How people know perturbation? Mrs. Endo, you know it. Yes. So, that is what we call a wave. You experience it every day. You can go home, take a bucket of water, keep it, just monitor it when it's settled, that it's not shaking. Carry one small, even a small paper that has a little weight, drop on it. What do you see? You start seeing ripples. Is it not? Huh? What will you see? You will see things moving like this, is it not? From the center where you dropped it to the end where you have the boundary. So we must have initial and what? We must have boundary conditions whenever we are trying to talk about these waves. Okay? Now, you will see in our MHD waves, there are 3 important waves we may consider. I know you know what is longitudinal waves. You also know what is transverse wave. And you also know your standing waves or stationary waves. The definitions are there, and I believe you'll be able to get them. The transverse or longitudinal, for instance, is the one that moves parallel. Is it not? In the direction of the propagation. It must be parallel to the direction of the propagation of the wave. You have the sound waves. You have the P waves, which are, P waves are actually compressional waves. They are mostly relevant in geophysics. And then most of us, when we talk about geophysics, we only think geophysics on the earth. The greatest studies on geophysics are there in the atmosphere. Geomagnetism. You know? So geophysics is not to look for oil or water. Those ones are called petrogeology and the hydrogeology. But real geophysics is in the atmosphere, where you have geomagnetic storms. All right. Now the standing waves, for example, or the transverse, you go back there, it's a disturbance that is perpendicular to the direction. So one is parallel, one is perpendicular. The standing or stationary, stationary tells you it must be what? Constant. It's what? Constant. It's a wave that remains in a constant position. So you will see the phenomena can occur when the medium is moving in opposite direction. So this is moving in the opposite direction of this. So they can collide. And their collision, because one is positive, one is negative, of equal magnitude, they tend to suppress each other to remain constant. Now, as a result of interference, you see, interference can cause standing wave. You see, they put this device for me in my pocket. I quickly removed this GSM because it's what? On. And I also have another device in my pocket. All of them control. They have electromagnetic. They have magnetism. They can fuse with this one. It will not function again. Because all these I'm talking are as a result of what? Wave. Wave insinuates sound. We're going to know that later. So, we'll see. Now, that is exactly the kind of situation we have. So we try to broaden our mind on waves. We have known that it's what? A disturbance. A little disturbance. And then that disturbance is very important for us. Now, next one. The next thing we'll try to look at, there are parameters that are associated with waves. So whenever you are studying waves, there are things you should know. One of them is actually what we call, like in a sinusoidal wave, there must be frequency. There must be a wave vector. And both of them at a time, of course. Because you can look at that as being proportional. You can look at your wave as a function of S and T to be proportional to E, I, K dot R, which are vectors, minus omega T. You have seen this kind of expression before. This is Fourier decomposition. How many of us, this is coming from Fourier series? This is complex because there is I. I there is imaginary number. So a wave is characterized by such an expression where you have the frequency. Most times, because it rotates, we look at this as angular. frequency. Then you have your wave number. Vector. It's a vector. Then you have your this. Now you can see we have K dot R. K as a vector, for example, could be K in the direction of X, in the direction of Y, in the direction of Z. And the R vector could be X, Y, Z. So you can do K dot R. K dot R will give you what? A number. Is it not? So that actually gives us, if you look at K dot R, will give you KX, KXX plus KYY plus KZZ. Is it not? So, you see what I'm saying? We should go back to our vector selector, and they will appreciate that. So, this is how a wave can be represented. This is the form we will use. But you also have a form of wave that will actually give you, say, Ux of t will give you A, which is the amplitude of cosine of omega t minus psi, which is the phase angle. Okay? This one is the phase angle. They are all sinusoidal in nature, that they go like this, where you have the wavelength, you have the amplitude, and so on. So that is one characteristic we should know about waves. And then we said it does what? It transports energy or information from the place it starts to another, isn't it? And then you should also know what is a period. These are fundamental things we should know, is it not? What is a period of oscillation? I will not tell you. Okay. What is an amplitude? The height, oh, not this way, oh, it must be. So you see that life is easy. You know, life is easy if we can go and refresh our minds and get some of these things before we start. We will do that today, and I believe all of us will be happy. Now, there is one very important aspect when we look at the characterization before we now begin to see how the wave parameter works. When we want to propagate a wave, we'll look at the system as it is. We disturb it a little and see what happens with that disturbance. Then, yes? Yeah, go ahead. No, you can sit down. You can sit down. Sit down. Time? Okay. No, go. No, the other one. No. Yes. It's a scalar. Huh? Sure. But you... No, when you get there, you will see. Because exactly what you have there, A, E, I, let me say phi, for example, is exactly like what you have. Or let me just use something different. Let's say this is an embodiment. Because this is a scalar. This also is a scalar. This, if it's more than this, is positive. If it is less than this, it's a negative, you see? So, when it's negative, it's what? Decay. Alright? But the presence of that idea, I, which is square root of minus 1, gives you all the phenomena you want. Now here, you remember here, you can use Euler to write this as what? A into cosine of omega, well, let's say of t or x plus I sine of omega x. For example, if you're looking at x, because if it's a function of, okay, let's say t, that's a t, that's a t. So, what is most important in the wave phenomena is the real value of A, E, I, omega t. Okay? The real value. So you see where your complex analysis is coming in, So we should all try to bring these things up. Now, before she called us back, we want to propagate a wave. We have disturbed the system from equilibrium. And we'll assume a Fourier, okay? Which will give us, the result will be in terms of frequency. That will lead us to what is known as dispersion relation. This dispersion relation actually will help us to write this. Omega will be equal to a function of the wave number. So you will now begin to see that whatever result you will get from the system will actually give you the wave number and what? Omega, for example. You can normalize it. We can also normalize it. And the next thing from this, when we get our wave, because the wave equation now comes as in terms of what? Omega. It will lead us to what is to get our phase velocity. It can also help us to get our group velocity. So you see, the phase velocity is the rate at which the phase of a wave propagates through space, and is given by that omega over what? K. So you can see, most of the time you can normalize this, and this becomes time, which is actually the phase velocity. So how will it look like? We say it's the rate at which that wave propagates through space. Then another interesting one is the group velocity. Now you see here, if omega over k is greater than 0, the wave is to the right. If it is less, it's to the what? Left. And then you will get to go, we'll see the interpretation depending on the work we're working. Because these are the things you will get from the set of equations you will get. All the equations you struggle to get from Maxwell's equation, from continuity equation, whatever, will lead you to what? Dispersion relation. It is there we will now begin to talk about the propagation of the wave. All right? Now the group velocity will be partial omega by partial what? K. And what does it tell us? Is the rate at which the overall shape or the wave amplitude propagates through space. It is actually this particular wave that carries the energy or information along the system. So you see? So you have solved the mathematics. We now want to see how. What is the physical interpretation? So these two things are very key. Phase velocity, group velocity. And we'll try to see that. Well, the next things are just some remarks. some what? Remarks. What gives rise to a periodic motion? Of the fluid? Because tomorrow morning you will give me all the answers. Don't use your phone to call people. Use your Google to find the solutions. Now, that's number one, coordinator. They will submit to you. Waves propagate information and energy through a system from one location to another. Is it true? Okay. A wave can be decomposed into different sinusoidal waves by the technique of Fourier analysis, even for a complex oscillations, as long as the amplitude of the disturbance is what? Small. You see, there's what? A caveat there. The transport or propagation is always will have what? A finite speed. The speed must be finite. You see why most times we try to ignore the speed of light? Because of application. All right. Now, small amplitude disturbances will lead to plane waves as long as the direction of the propagation and amplitude remain the same everywhere. The other one is waves are closely related to shocks, instabilities, and turbulence. You know, most of us, when you travel by air, when your plane start doing like this, they will tell you there is turbulence. Fasten your what? Seatbelt. So that you will not follow and move. Is it not? Aha. So after this period, in case we will start again, or you will be working with me or with any other person in collaboration, the next thing is shocks, instabilities, and turbulence. You see, we have equilibrium, we have the wave, we have equilibrium, wave, shocks, turbulence, and instabilities. These are the areas that are characterized. They are very important areas in our work. Now, waves are everywhere in magnetized plasma as well as in the air, as I was trying to tell you before. So this is not part of our work. But because of reconnection problems or phenomena of reconnection, waves or magnetic fields move from the north pole, and look for the south pole. And then from south again, it goes back to the north. That one has connected. Another one will go, but they don't cross each other. Now, what are the importance of reconnection? Let us not go into the physics now. Let us look at in our virtual life. Have you ever walked on your tile or your floor without your shoe, without stockings before? Particularly when you are sick. You try to walk without wearing anything on your floor. Have you done it before? And after some time, what do you have? If it is high temperature, it starts coming down. What does that tell you? The reconnection of magnetic fields has a healing power. So most of us try it most times to walk barefooted. Particularly when you go back from work, you see a lot of stress on your legs. Remove your shoe, walk around. Now, those of us that are in coastal regions, we normally experience flooding. 90% of flooding in coastal regions are caused by magnetic fields. When they try to move, to reconnect, if there is a kind of disturbance that pulls, you need to have magnetic storms. So that is the thing. So there are quite a lot of things, physics and waves and magnetic fields have for us to study. And then I think by tomorrow, by God's grace, we'll start looking at simple wave equation. Maybe I can give you that as an exam, as a homework. Do we run like Tracy? Or after tomorrow? Huh? Is it? Okay, they'll have their note. But this one is from 400 level. Okay, don't worry. They will have it. Okay. So I think tomorrow we'll start with ordinary waves and then see how it goes. Then after that introduction, that may take us like 30 minutes, we will now begin to talk about hydrodynamic equations. Then I may ask all of us here, have we done fluid before? Have we done fluid dynamics before? Hydrodynamics? Huh? Huh? Okay, they did it in engineering. Huh? No! In my university, we talk about waves, we talk about fluid. But what happens is that fluid dynamics is not difficult. It's one of the simplest areas in mathematics. But it will require you to have some basic mathematics. You will enjoy it. Because fluids, if I ask you a definition, what is a fluid? What is a fluid? It flows easily. I'm hearing that one too. Okay. Oh. Okay. You see, liquids and gas. A is an example of a fluid. Is it not? A is what? An example of a fluid. Water is a fluid. All gases are fluids. But we have compressible fluids, which consist of gases. We also have incompressible fluid that is like water. Is it not? So these are things we'll try to look at. In our own study, we'll look mostly into compressible fluids because the atmosphere is consisting of plasmas, and these plasmas are ionized gases. So we'll try to develop simple equation of continuity because the fluid is being driven. There's an equation of motion. Is it not? And then because we are going to couple magnetic field to it, there will be magnetic induction equation. And of course, ID gas law. So we have 4 equations that we will get. And in these equations, there are components. Each of the, the momentum equation will have 3 components. And then we'll go on. So we'll get through that when you get your note. My note is simplified that you can read and expand on it. There won't be difficulty. So, fluid. Take your goggle. Define a fluid. Find the definition of a fluid. Find the definition of incompressible fluid. Find the definition of compressible fluid. All right? Then we'll be in business. I think today we will end and we'll start with 1D tomorrow. We will start with 1D. The coordinator is giving me the go-ahead order to exercise his rights. And his rights is that I must make you to understand. Is it not? This is 1D wave equation. So if you can look for the solution, I'll be happy. That says partial 2u by partial t squared equal to c squared partial 2u by partial x squared. That is 1D wave equation. It's always done in year 4. Is it not? It's part of Schrodinger's wave equation. Is it not? You can reduce your Schrodinger's wave equation to this, and you solve it by separation of variables. So all you need is a little knowledge of partial differential equation to solve hyperbolic function equations. Is it not? So we'll try to start from here tomorrow, and it wouldn't take us 10 minutes. Then we'll now begin to look at hydrodynamic equations and see how they will help us to talk about sound waves. We'll start from there tomorrow. I think today we have ended.